Today we will be doing ionic equilibrium. You all know, thanks to the acid bases salts chapter of class 10, you all know that the acids and bases can be strong, they can be weak. For example, you know from your knowledge of class 10 that acetic acid is a weak acid. So acetic acid will dissociate in solution. Acetic acid will dissociate in solution to give acetate ion and H plus ion. And one more thing is that the dissociation will be a very small percentage of the original concentration, unlike strong electrolyte like HCl, H2SO4, which are expected to have 100% dissociation. Acetic acid dissociation will be very insignificant. So that is why it is a weak acid. Now suppose the initial concentration of acetic acid is C, molar concentration is C, and these two, they both are 0. So let us say that the degree of dissociation of this particular acetic acid is alpha. So at equilibrium, the concentration of acetic acid will be C into 1 minus alpha, and acetate and H plus will be C alpha, C alpha. So the equilibrium constant will be C alpha into C alpha by C into 1 minus alpha. That is coming C alpha square by 1 minus alpha. Now alpha is the degree of dissociation, and I told you that it is a very small value. So we can take 1 minus alpha approximately equal to 1. So we will get Ka is equal to C alpha square, and alpha will be equal to root over Ka by C. So Ka is called the dissociation constant. A is because it's an acid, and the degree of dissociation is root over Ka by C. Now you will notice in this expression that if C is very low, if the concentration is very low, then alpha will be very high. That means to improve the dissociation of a weak electrolyte, we must make it as dilute as possible. So if C is very low, then alpha will be very high. So according to the law, the name of the law is Ostwald's dilution law. So according to Ostwald's dilution law, the degree of dissociation of a weak electrolyte can be increased by making the solution as dilute as possible. This is known as Ostwald's dilution law. Now the thing is, this particular reaction, as I have been telling you, that acetic acid is acting like an acid in this reaction. Why? Because it's donating a proton, and after it loses a proton, the substance that is left, that is acetate ion, it will become a base, and we call it the conjugate base. So acetic acid is the acid, and acetate ion is called the conjugate base. So the conjugate base of an acid is basically the base which is obtained by the loss of proton from the acid. Now consider this reaction. See, this is the opposite reaction. Acetate ion is accepting a proton to become acetic acid, and since acetate ion is a base, it is releasing OH minus ion in solution. So this is the opposite reaction. So coming back to the dissociation constant for this reaction, for the acetic acid dissociation, the dissociation constant will be given by this expression, and for the second reaction, we can say the dissociation constant is Kb, because this is a base. Now you will notice one thing, that I have not considered the concentration of water. You see, all these solutions are in water, they are all aqueous solution, and water is the medium, so it is considered to be in bulk quantity. So the concentration of water is not considered in the equilibrium dissociation constant. So we have got Ka, we have got Kb, and if we consider water alone as an electrolyte, then this will be the reaction for dissociation of water. So the dissociation of water, the reaction is H plus into OH minus, and as I told you, we will not be considering the concentration of H2O. So the dissociation constant of water is H plus into OH minus, and this we can also write it as Kw, because this is for acid, this is for base, and this being water, which cannot be truly speaking considered either acidic or basic. Now this particular expression is called ionic product of water. So this is called the ionic product of water, and it has a constant value at 25 degrees Celsius. It is equal to 10 to the power minus 14. So this is the value of the ionic product of water. Now you will notice one thing, that if you multiply Ka into Kb, then it will come equal to the ionic product of water. So Ka into Kb is equal to the ionic product of water, right? So this is a very important result, that whenever we consider a conjugate acid-base pair, the product of Ka into Kb is equal to the ionic product of water. Now one important thing is, you know that pure water is neutral. So because pure water is neutral, so at 25 degrees Celsius, the concentration of H plus or OH minus, both are 10 to the power minus 7, right? Because pure water is neutral, so at 25 degrees Celsius, both these quantities are equal to 10 to the power minus 7. So if you have an acidic solution, then what will happen is that the concentration of H plus will be more than 10 to the power minus 7, and if you have a basic solution, the concentration of H plus will be less than 10 to the power minus 7. Now there is a scale known as pH scale. pH of any solution is the negative logarithm of the hydrogen ion concentration. So pH will be minus of log H plus. So if the solution is neutral, then pH will be 7. If the solution is acidic, then pH will be less than 7. And if the solution is basic, then the pH will be greater than 7. Not only that, whenever a solution is acidic, the hydroxyl ion concentration will be less than 10 to the power 7. And whenever a solution is basic, the hydroxyl ion concentration will be more than 10 to the power minus 7. So just like we have pH, we also have pOH, which is the negative logarithm of OH minus concentration. This is called pOH. So if a solution is neutral, then pOH will be 7. If a solution is acidic, then pOH will be greater than 7. If a solution is basic, then pOH is less than 7. So these are the different parameters of judging the acidity or the basicity of any solution. Now at 25 degrees Celsius, the product of concentration of H plus into concentration of OH minus is 10 to the power minus 14. So if you take negative log on both sides, then you will get a very important relation that pH plus pOH is equal to 14. So this is a very, very important relation between pH and pOH. Now let us consider, once again let us go back to the dissociation of acetic acid. As you know that acetic acid will dissociate to give acetate ion plus H plus. So suppose the initial concentrations are these. Now in this if you add in this reaction, in this mixture, if you add HCl, you know HCl is a very strong electrolyte. So suppose the concentration of HCl is C dash. So after dissociation, the H plus which comes from HCl, the concentration will also be C dash. Now in this reaction, we can say that the equilibrium constant rather the dissociation constant is equal to this concentration of acetate into concentration of H plus by concentration of acetic acid. So this is coming C alpha into C alpha plus C dash by C into 1 minus alpha. Now remember, at a particular temperature, this particular value Ka will be a constant, right? But in the numerator, in hydrogen concentration, there is one extra term C dash. Now Ka is constant and C dash is an added quantity in this hydrogen ion concentration. So that means to keep Ka constant, since the concentration of hydrogen has gone up, alpha will go down. That means the degree of dissociation of acetic acid has decreased by adding HCl. And why did this happen? Because HCl has a common ion H plus with acetic acid. This particular phenomenon is known as common ion effect. So common ion effect says that the degree of dissociation of a weak electrolyte can be decreased by adding to its solution a strong electrolyte having a common ion. So in this case, the strong electrolyte is HCl and the common ion is H plus, and due to the addition of HCl, the degree of dissociation of acetic acid has decreased. Now you know that some salts are highly soluble and some salts are almost insoluble. So those salts which are insoluble, they tend to precipitate out of the solution. Like for example, AgCl is such a salt. Now if you consider the dissociation of AgCl, so AgCl is not a salt which will dissociate. In fact, it tends to precipitate out of the solution. So in the dissociation of AgCl, since the dissociation is very, very poor, there will be an ionic equilibrium between the ions and the undissociated salt, right? So this is also an example of chemical equilibrium. Now if you consider the product of concentrations of Ag plus and Cl minus, then this product is denoted by KSP. KSP literally stands for solubility product. So once again, whenever there is an ionic equilibrium between the ions and the undissolved electrolyte, in that case, the solubility product is equal to product of the concentrations of the individual ions. Now, if we want to take a general reaction, we can say that AXBY is the salt. It's solid, and after dissociation it is expected to give these ions. So the solubility product is equal to concentration of A to the power X into concentration of B to the power Y. So this is the formula to find the solubility product. Now let us say that at ionic equilibrium of this reaction, at ionic equilibrium, let us say that the molar concentration of AXBY is S. So this is called solubility. So let us say that the molar concentration of AXBY, which we call solubility, is S. So these will be XS and YS. So in that case, KSP will be xs to the power x into ys to the power y so it will be x to the power x into y to the power y into s to the power x plus y. So this is the very useful formula to find out the solubility product. Like say for example, if you are analyzing this reaction, suppose if you are analyzing this reaction, in that case the solubility product will be 2s whole square into s, that is equal to 4s cube. Now let us say that this reaction has not yet reached ionic equilibrium. Suppose the reaction which we are considering, suppose this reaction has not yet reached ionic equilibrium. In that case, this particular product will not be called solubility product, it will be called ionic product. So in case the reaction has not reached chemical equilibrium, this product will be called the ionic product. So if the ionic product is equal to solubility product, that means the solution is just saturated and no precipitation takes place. If ionic product is greater than solubility product, solution is supersaturated and precipitation takes place. If ionic product is less than solubility product, then solution is unsaturated and more solute can dissolve. So this is the details about the topic solubility product. So what we will do is, since this is a big chapter, we will continue the rest of the chapter in our next session. So that brings us to an end of this session of ionic equilibrium.